Okay, good morning, good afternoon, or good evening, depending on where you are. Welcome to the third in a series of free webinars on premise plumbing modeling. Today's topic is modeling water demands in premise plumbing systems. My name is Steve Buckberger. I'm on the faculty in the College of Engineering at the University of Cincinnati, and along with my colleague, Miriam Bloker, from KWR Water in the Netherlands, we'll be jointly hosting today's event. Of course, relying on the skill set from Bill Platten and Paxton at EPA. So I saw we've got about 30 folks already tuned in. We're glad you're able to join us for this 90-minute flight. And in today's flight plan includes 4 presentations that will take just over an hour. So you can see the 4 presentations. I'm the leadoff hitter here. And I'll be talking about estimating peak demands, followed by Jim Lutz, who will focus on the hot water demands in premise plumbing. Then we're going to cross the pond to Miriam Blocker, who will talk to us about her Simdium model for simulating water demands in buildings. And we're going to wrap up with Stefano Alvisi in Italy on the impact of the COVID-19 pandemic on water demands in Italy. When we wrap up the speakers, then we're going to be joined by 2 panelists, Toju Omohomi, who's an ORISE participant at the US EPA, and Jonathan Burkhart, also at US EPA. So we'll have a panel of 6 of us that can hopefully address any questions that come up. So in that remaining 20 minutes, too, I did want to emphasize that the audience, you'll help us fly the plane, so we'll open it up for questions and so forth and suggestions. I also want to take just a minute to let you know the school year is not too far away, and so we're taking the liberty today to try something different. We're going to close today's event with a short quiz. It's going to be comprised of 4 simple multiple choice questions, 1 from each of today's speakers. So no need to panic. I don't want anybody skipping class yet. The quiz is optional. And we'll give more details for interesting quiz takers or interested quiz takers at the end of the hour, okay? So, and I also imagine that there's going to be a parallel universe that's going to run concurrent with the active chat room, the thread. And that's fine, and we encourage that interaction. But please remember to save some of those good questions for the panel session. Now, before I start my presentation, I did want to give you some brief background information. So let's see if I go to the next slide here. Here we go. Right, so this webinar today is being organized by the ASCE EWRI Task Committee on Premise Plumbing Modeling. It was formed last summer. We've got about 8 members on the executive committee and many participating members. In fact, anyone who's part of the email distribution. So we have some real strength in numbers. The objective or the purpose of the Premise Plumbing Modeling Task Committee is threefold. We really want to advance the science of this new field, and we're going to do it 3 different ways. We want to document the state of the art, identify future research and development needs, and prepare a report and perhaps other mechanisms for disseminating information. One of the ways we're disseminating information is running a series of webinars. You can see we're already at webinar number 3. We've had 2. Today's, of course, water demands, as I mentioned. Next month is going to be on hydraulics, followed by monthly webinars thereafter. Okay. And then last, I want to mention here, if you are interested in more information, please feel free to reach out to Junsuk Lee. He's the task committee chair on the faculty at Manhattan College, and you can see his email address there at the bottom of the page. So without any further ado, I'm going to jump into the first presentation, which has to do with estimating peak water demands, or my slogan for today is Hunter's Curve meets the 21st century. So question is, why are we interested in peak demand? And it turns out peak demand, you could argue, is perhaps the most important parameter for sizing a premise plumbing system. You need peak demands for the service connection, for water meters and heaters, softeners, and all sorts of hydraulic appurtenances. And if you think about this problem for a minute, it's actually rather challenging. Here, for instance, is a time series plot of real data from midnight to midnight, measured from 21 different homes. So this is virtually instantaneous information. And if we're interested in the peak demand, we might notice that sometime around the supper time hour, we hit a peak of about 60 liters per minute. So maybe we're talking 15 GPM for here. And the question might come up, well, is that a representative value for the peak demand? Well, we know we're dealing with a random process. If we came back the next day, we'd have a different value. And if we came back the day after, we'd have yet another different value. So it's really dealing with random variables here. And this was first recognized about 80 years ago by Roy Hunter when he published his document on estimating loads in plumbing systems, part of the National Bureau of Standards. And Hunter recognized that there were really three key characteristics that we had to pay attention to, the NPs and Qs. N, of course, is the fixture count. That is, how many fixtures do we have in the building? P is the probability of use, especially during the peak period. That's typically a dimensionless ratio of the time the fixture is running divided by the time between fixture uses. And then we've got fixture flow rate. So the NPQ parameters are really important, and they're going to be, I'm going to refer to those quite often throughout this presentation this morning. So Hunter's work focused really on parameters, and I'm hearing a little bit of background noise there, so please mute yourself. And he focused on the flush valve, the flush tank, and bathtubs. And you'll notice here that he was able, from measurements in the field, to get estimates of P values. For example, a 3% chance that a flush valve would be on during the peak use, and it ran at a rate of 27 GPM. So we managed to obtain these values for these three fixtures, and also included an intriguing metric here called the fixture unit, kind of a mysterious thing. And in a minute, we're going to see why he was compelled to include something called a fixture unit. So let's see how Hunter thought about this problem. And I'm going to pick on the flush tanks, the flush tank toilets. And I'm going to assume we're dealing with the building that's got 100 of them. And remember from the previous slide that the probability of use during the peak hour was about 20%. Well, it turns out that we can build a binomial distribution that tells us the number of busy fixtures, in this case, flush tanks, during the peak hour. And so what we see on the x-axis is numbers from 0 to 100, but a lot of activity from around 10 to 30, with the highest, the mode, occurring at 20. So that's the most likely number of busy fixtures. And if you think about that value, really, it makes a lot of sense, because we've got 100 fixtures. The probability that any one is on is 20%. So the product of those two, 20% of 100, gives us about 20 fixtures that we would expect on average to be running. But it's a random process, so we could have something lower, something higher. But it's interesting here that even in a building with 100 tank toilets, we don't have to design for 80 or 60 or 40 of them to be running at one time. We have to design for some number less than that, because there's virtually no chance that we go above, say, 30 or so. Well, how did Hunter solve this problem? He introduced a design threshold called the 99th percentile. He said, I'm going to size a system that handles the loading condition that demand 99% of the time. I won't worry about the extra 1%. If we go above that, it's not catastrophic failure. It just means I've got a little bit higher head loss than I'm expecting. And so maybe it takes a bit longer for fixtures to fill and so forth, but the service would still be provided. And I'm always amazed when I think about what Hunter did here, because he was really 20 years ahead of any other agency in the federal government, because it was 1960, 20 years later, before the 99th percentile came along with FEMA, who did this with the 100-year floodplain. So Hunter was doing this 99th percentile as his design threshold, back in 1940. And you can see that the 99th threshold in this case is 30 simultaneous tanks that are running, each running at 4 GPM. So we might argue, okay, the design discharge here is 120 gallons per minute. Simple. Well, what happens now if we introduce a second type of fixture? So I've got the blue fixtures that we just looked at, and now I've got the red fixture group. And let's just suppose here, and this is a hypothetical, that this fixture group operates with a p-value of about 40%. Well, now I can go ahead and I can say, well, let's get the 99th percentile for the red fixtures. In this case, maybe it's close to 52 busy fixtures. and they're operating at, let's say, 3 gallons per minute. So I would expect a draw of about 156 GPM from the red. Oh yes, I've got the blue coming in at 120. But what do I do with that? Do I add both of those values together to get my design discharge at 267 GPM? It turns out that is not the correct way to approach this, and Hunter recognized that. And the reason for that is because if we did that, it would really be over-designed, because you would be assuming that you'd have these 99th percentile events occurring simultaneously at these two fixture groups. So we really had to find a way to put these fixtures together, to combine them into some sort of overall representative building response. And Hunter did that by introducing fixture units. And so we saw that earlier. We had the tank had fixture units of 5. We had the bathtub was 4, and the flush valve was 10. And these fixture units are kind of mysterious, but they're really a common current that allow us to add together the loading impact of a variety of different fixtures in buildings. And when we add that number up, we get a value that we can use on the x-axis of this iconic Hunter's curve, and then go over to the y-axis and read off the 99th percentile for that particular building. So this was a phenomenal achievement in engineering. And a number of folks have claimed even that next to the Moody diagram, the Hunter curve has probably been the most useful hydraulic design curve of the 20th century. Now, however, if we look at, say, a point that might exist in 1940 and we bring it to the year 2020, what we find is that it's really no longer on the curve. And so what's happened is over time, Hunter's curve has been faulted for tending to overestimate or be overly conservative for peak demands. And why is that? Well, it turns out that Hunter's curve is very simple, very effective, but that's also seductive. And so it's been applied in a number of instances for which it really wasn't intended, number one. And then number two, hey, let's face it, times have changed. You and I use water differently than our grandparents did, and fixtures are different. We've got not only different habits, but we've got water conserving fixtures. And so, for instance, one approach or one condition that Hunter assumed in his development was that we had what are called congested conditions. And congested conditions assume that we have really a queue of people that are lined up to use a fixture. And this is the kind of thing that you might see, for example, at halftime at the basketball game, or intermission at the symphony. But when we apply it to situations where congestion doesn't exist, we get over-design. And by the time we get to the 1980s, 40 years after the Hunter's curve was introduced, classic engineering plumbing textbooks were saying, hey, folks, it's safe to reduce the values obtained from Hunter's curve by 40%. So there was this recognized need that it was overly conservative, but no attempt to really go back and update it or change it. This also led, incidentally, to a proliferation of different Hunter's curves, and so modified Hunter's curves that applied to all sorts of different uses. You've got restaurants and nursing homes and houses and apartment buildings and so forth. Now, beyond that, there's another professional group that took a slightly different path, and I just want to take a second and include it here. AWWA branched out and introduced a new type of design chart, not based on fixture units, but if you look at the x-axis, you'll see they're based on fixture values. So not confusing, right? What's the difference? We saw Hunter introduce the mysterious fixture unit concept. Fixture values are easier to understand. If you take a look at a building with a number of fixtures and you ask yourself the question, if I activated every fixture in that building, if I turned it on, what would be the flow rate, assuming that all those fixtures could run independently? And that would be the total demand for the building. So that becomes the x-axis. And then on the y-axis, we empirically plot observations from the field. So if we go out and we obtain information on peak demands for buildings, we can build a graph like this, and then we can establish envelope curves, and you see two of them here, envelope curves that we think represent the 99th percentile. So there's one on top for the flush valve, there's one on the bottom for the flush tank, and this is actually the approach that's taken in M22. currently in revision, but it's again, it's a valid approach. This also, incidentally, is a very common approach used across the pond in Europe. Now, we know there's a lot of issues when we are dealing with oversized plumbing systems, high construction costs, inaccurate metering, wasted energy, and so forth. I won't dwell on this. I will instead point out that a task force was established a couple of years ago with ASPE, IATMO, and the Water Quality Association to revisit Hunter's curve. And the mission of this task force was to establish a probability model to predict peak demands, really bring Hunter's curve into the 21st century. And we were lucky in the sense that we had lots of data. We had 60 cities with over 1,000 households, almost 1 million water use events. And with this information, we reestablished estimates for the p-values. Remember, we talked about the p-values earlier. So we've got, in this case here, p-values that are as low as 0.5% during the peak hour. That's for a dishwasher, or as high as 5.5%. So really an order of magnitude variation between the minimum and the maximum p-values given in this chart. Now, what's interesting is if you compare that to what Hunter had, if, for example, here with the water closet, that the flush tank had a probability of 20%, where we have an updated probability of 1%. So a tremendous decrease in the p-value, and the flow rate dropped from 4 to 3. And again, this is for a typical residential use. We don't have congestion, so it's not surprising to see 20 drop down to 1. So this is a plot that shows the NP plane, kind of summarizes some of the results that we've got from our analysis. And what we see here is 3 different colors, green, yellow, and red, that correspond to different algorithms that are going to be used depending on the size of the building. And then you'll notice here we've got Hunter numbers ranging from 0.2 to 1, 5, and 25. And I want to just say something briefly about these Hunter numbers. The Hunter number is a term we've introduced. It's defined as the product of N times P. It's got a really nice physical interpretation. It's really the average number of fixtures that are in simultaneous use during the peak demand period. So in the case that we looked at earlier with 100 flush tanks and a probability of 20%, the Hunter number would be 20. And it turns out that there's an interesting connection between stagnation during the peak period and the Hunter number, and that stagnation is connected in the following expression here. The exponential function to minus the Hunter number, it turns out, gives you a really good estimate of stagnation, and we can see that in this plot. Now, so we'll refer to that from time to time. So what I've shown here now is returning to this diagram that shows this shaded area that identifies the range of interest for probabilities of use from about 0.5 to about 5%. And we've got size of buildings from 1 to 10,000 fixtures. And then these lines across here are lines of constant Hunter numbers. So I've got Hunter numbers of 0.2, 1, 5, and 25. And remember, that physically represents the number of busy fixtures that we have. And then down at the bottom, we've got probabilities of stagnation. So in small, even during the peak period, in small buildings, we can have relatively high stagnation probabilities during peak hours. But when we get to the red zone, we've got high Hunter numbers, and almost no stagnation ever occurs during the peak period. Now, so what we find is we've got 3 different building sizes. We've got some different algorithms that we have to use to estimate the peak demand, because we have in small buildings, we've got to talk about discrete fixtures. When we have large buildings, we can really use more of a continuous type of a numerical approach. And so this is a summary table from the new draft of M22 that's coming out here in the near future. I'm going to illustrate this with a couple examples. Here's from the red zone. So this is a large building. We're using something called the Wistort method, which is proposed by Bob Wistort about 25 years ago. Bob Wistort recognized that we had this very nice distribution of busy fixtures that we saw earlier in this presentation, and it closely approximated a normal distribution. So Wistort said, why not use the normal approximation for the binomial distribution and select the 99th percentile to identify the peak demand? And so this is exactly what he's doing. So you'll see here we've got, in this case, the 99th percentile is given by this expected value, and then we've got the variability here. And if we grind through this, we get, at the 99th percentile, about 30 fixtures. So nice agreement with what Hunter came up with. And again, this is our normal approximation for the binomial distribution. So we just visited what would be the red zone. Now we're going to take another look at the green zone, and this is an area what we call exhaustive enumeration. So in the green zone, which are smaller buildings, we can't really use this normal approximation, and instead we have to take a look at the individual effects of each individual fixture. And so what we find here with just one fixture is there are just two outcomes. It's either on or it's not on. With two fixtures, there's 4. With 3 fixtures, there's 8. And I think you get the idea. It grows as 2 to the n. And so essentially what we can do is we can identify through exhaustive enumeration all the possible combinations that might exist. And we can plot this cumulative distribution function again, as long as the number of fixtures are not too big. And I can put together this probability plot that shows the 99th percentile and the demand discharge for any combination of fixtures in these small settings where I don't have a lot of fixtures I'm dealing with. Now notice there's two possibilities here. There's a blue line and there's a red line. The red line is really the one that we want to deal with because we're not really concerned with this case over here at the edge where there's no fixtures on at all. We're only going to be designing for the situation where we have flow and we have fixtures running. Now the problem with this approach, it is exact, is that it blows up on us numerically. It grows as 2 to the n. So as soon as we get to 30 fixtures or so, we've got 10 million options that we're considering. So that's why we've got to slide over to some other possibility, like the case with Wistort's model. So just to summarize, what we have just saw here is that we've got on the left-hand side very few fixtures where we're using this example that we just saw. And then we've got on the right-hand side many fixtures where we've got Bob Wistort's summary or Bob Wistort's approach for estimating peak demand. And it turns out that what we've done to allow us to use these, and of course in the middle with the yellow, we've got this transition that goes from few fixtures to many fixtures. We've introduced something that's called a water demand calculator that really takes these three possibilities and performs all the calculations for us. So what we see here is a case where we've got a house where we've got values that we can put into the cells that are in white. We enter the number of fixtures. And then we've got the probability of use for those. And then we've got the fixture flow rate. And then when we execute this, it will give us the 99th percentile. So just to illustrate this, here's a case where we'll go with the green zone, where we're down with exhaustive enumeration. And we've got a case with 12 fixtures in a house. The Hunter number is about 0.3. And so when we put it in, we find, gee, maybe I've got 2 combination baths, I've got 3 faucets, I've got 12 fixtures. And when I grind through the water demand calculator, what we find is I've got a 99th percentile, in this case, of about 11 gallons per minute and a Hunter number of 0.3 and so forth. So now if we use the Uniform Plumbing Code, UPC, for this example, we would see that it would push us out to about 18 gallons a minute. But in this case here, where we've got these flows with and looking at the 99th percentile, we're down at about 11 GPM. Now, we're really more interested, though, in larger cases. So let's consider here something out in the red zone where I've got now 1,200.
Hey, Steve,
yes?
You're pushing time.
Okay, let me wind down real quick. So hey, thanks, Bill. So in this final case, we've got this a 5-inch line that we would need here for a building that's got, in this case, about 1,200 fixtures, 62 gallons per minute, and so on. So we've got this methodology that's available to us. We've got some examples that we've used that works out well, and we can employ and use this in the building information model and so forth. So let me just summarize by saying in my final slide here, This peak demand is crucial for premise plumbing systems. We know that the demand is a random process. We've updated Hunter's iconic curve, brought it into the 21st century with the water demand calculator, and we've made good progress, we think, in the residential sector. But we really haven't made much progress in the non-residential sector. So that's where we've got to get some information for non-residential. We need a coordinated effort really from government agencies for non-residential buildings. So I went a little bit over, got carried away, but thank you for your attention. We've got time for questions at the very end, and we're going to turn this over to the next speaker.
Right, Jim Lutz.
Yeah. So Jim, it's all yours.
Okay. I want to talk about a subtle distinction, but hopefully you'll get it when I'm done, between the demand of hot water and the use of hot water in premise plumbing systems. Sure. Okay. This is a cartoon, but it's to get you to think of what a domestic hot water system is like. I'm focusing on the hot water side because for personal historic reasons, but that's my specialty. And the key thing to remember is that the demand is caused by people. So, if you don't have people, you should not have any hot water. You wouldn't expect any hot water in a residential building. So the people use a fixture or an appliance. The appliance pulls in, a shower, a sink, a dishwasher, a clothes washer, whatever, a bathtub. The fixture pulls in hot and maybe cold water and maybe energy, and then the water is pulled out of the water heater. The hot water is pulled out of the hot water heater, so you got to factor that in if you're doing energy calculations. And after the water is used, it goes down the drain and off the property boundary. So next slide. Again, the sort of patterns, the same stuff. This is annual total water use, and any time you're trying to figure out what's going on with people using water, you end up with a distribution that looks something like this. There's a peak sort of down close to the bottom, and hopefully it goes to zero when you don't have anybody there. And then it tails off and tails off and tails off. So that's the question Steve was just talking about, is how do you find the 99% when you're using it for sizing? If you're using it for operations and energy calculations or water budgets or things like that, you're probably going to be down more near the peak. And these patterns are not normal distributions. They're closer to log normal or something like that. Next slide. So and I'll stress this again, it's the people that use hot water. If you don't have people in the house, you really don't expect to see any hot water. You don't have people in the house, you may see some cold water if they have an automatic irrigation system or something automatic. But without people, you should see zero. With one person, you'll see about 15 gallons per day. And two people, it's, about twice that. It's not quite linear. It actually sort of levels off as you get more and more people in the household. And then the tail end, there's so few households like that have been measured. The distributions are not real normal out there. Next slide. It turns out the age of the occupant matters. If you're designing a building and you don't know the age of the occupants or the expected occupancy pattern, you can't account for this. But if you're trying to do a specific type of building with a specific population, then you may want to account for it. But the stories about the teenagers staying in a shower for an hour or so at a time, well, that's true, at least statistically. And little kids who can't reach the faucet don't use as much hot water. Next slide. And that's statistical. You know, you'll get some, even with in those age groups, there's still those distributions of use. The other thing about houses is they're old. About half of the housing units in this country at least were built before 1980, before all these plumbing codes really started kicking in. So what you're actually going to end up using in your plumbing system and materials and flow rates of the fixtures, it depends on the age of the building. The other thing to note is people move around a lot. This was before COVID, but you know, I don't know if it's changing now or not. Next slide. This is the way Title 24, which is the Building Energy Efficiency Standard in California, we're doing something on this for compliance here. If you're planning on, if you're doing code compliance for a house that's going to last 30, 60, 100 years, how do you plan for how many people are in there? So this is looking at, for the number of houses or housing units by number of bedrooms, how many people are in that building statistically. So for a 3-bedroom house in California in 2009, there was a 37% chance that 2 people lived in a 3-bedroom house. Or, there was actually an 8% chance that 5 people were living in the house. So when you're trying to do compliance and figure out what a building is, how many people are going to be in the building over its lifetime, these are the sort of things you need to account for. Next one. This is from a study, a meta study that I did about, it's getting on 8-10 years ago, where I collected hot water draw pattern data, field data from lots of studies. So this is number of draws per day by the total daily volume of hot water. And that's 22,000 days plotted. And you'll see that there's a pattern, but there's lots and lots of scatter. And just to keep coming back on that, people use hot water in strange ways occasionally, but most of the time it's fairly predictable. Next slide. This, if you look at the house configurations, which is individual houses, not individual days, you still see that pattern that, some households are heavier hot water users than others. And again, there's outliers, but a general pattern. Next. However, 1 day's worth of hot water, and I'm sure Miriam will talk about this as well, it's lots of short draws. This is actually a high use day. They took 4 showers, used the dishwasher, used the clothes washer a couple times, no baths, lots and lots of faucet use. So this is actually a heavy day, but you can see even on a heavy day, even on the peak period time, either at the end of the day or the beginning of the day, there's still lots of stagnant time. Next slide. This is from the Reuse 2 summary of it on the hot and cold water use, looking at the individual uses that use hot water. The whole house is mostly cold water, but about a third hot water maybe. The mixture varies by the type of use. In the US, and probably Canada too, our dishwashers, we hook them up to hot water only, no cold water, which is different in other places. Faucets are about half hot, half cold. Showers are predominantly hot with a mix of cold to keep it the right temperature. The clothes washers, some are set to all cold, some still have some hot water use. Next. This is the data collection that Aquacraft uses. This is for the whole house water. It's a data logger attached to the meter. They run it for 2 weeks at a time, record how much water flows every 10 seconds. That's the same data, I believe, that Steve and Dan used for their, and Toju used in their analysis. Next slide. And with that sort of data at 10-second intervals, you can identify the end use by the flow, the pattern of the flow. The green ones were identified by toilets. The blue was clothes washer. The yellows were faucets, and the reds were, the one on the left is a tub shower combo with a diverter. So you can see they use the tub spout to flush the cold water out of the line before they got into the shower. In the stall shower, they weren't able to do that. Next. This is where we get, I'm trying to apologize for the text being so small. The difference between demand and use. The demand is, we want hot water services. We want clean bodies. We want clean water. We want clean dishes. And some of us like to get the benefit of relaxation or refreshment from showers. That's what we want. The hot water use, all these measurements, nearly all of the measurements of hot water use have been made at the water heater, not where the people are actually using the hot water. So that's a distinction that makes a difference. In the next few slides, we'll talk about it. What we want from our hot water use is not what the domestic hot water system necessarily supplies us, so we modify our behavior to account for that. And especially for showers and some sink draws, that may end up meaning more hot water is pulled from the water heater than we actually end up physically using. And that the hot water use measurements, even the ones Steve's calculations are based on, include that extra hot water. So we may want to come back to that, Steve, at some time. In North America, dishwasher water is often heated twice. It's heated, put into the pipes, cools off in the pipes, and then the dishwasher calls for it, and it's not hot enough, so the dishwasher has to heat it up again. So, and again, the hot water plumbing design is based on our hot water use, which we measure at the water heater, not at the shower head or the faucets. Next slide. And then here I'll take it into bits and pieces. So the impact of the distribution system, the hot water distribution system on showers. For showers and baths, we want the temperature around 105. We won't use it, especially for a shower, unless it's hot enough. I mean, maybe some people do, but most people don't. And we waste the hot water that's been heated in the pipe from the last use if it's not hot enough. And if we've got a really bad system and we know it's going to take a minute to get hot water to the shower, we may go off and do something else while the hot water is getting there, and we may not get back until hot water's been flowing out of the shower head for a minute or two. And the tub fill rate, and Steve's probably heard this, is what's used in the main driver for some of the pipe sizing calculations because it's such a high use. And it may not have to be that high if it's at, if you don't, does it really need to be 5 GPM? Could you be 4? And would people get upset because of the difference in time? And that might have an impact on pipe sizing, which would in turn maybe reduce this waste. Next slide. Here's an example. It's a very busy slide of shower draw with the tub spout. And this was a project I was involved where we measured the water temperature and volume leaving the water heater and the water temperature and flow rate at the shower head. So the top graph on this one is temperature, the bottom is flow rate. And for the up from about 7 to 721, hot water is leaving the water heater. It's hot at the temperature. It's almost 50 Celsius, and the flow rate, the gallons per minute, is up 1.4. This is as it's leaving the water heater. It takes until just before 722 for the water for the user to turn on the shower. And so there you see just before 722, the shower turns on, the temperature at the shower head jumps up, and then till about 723, there's various flow rate and temperature adjustments, and that's probably the person adjusting the temperature to their use. After 723 till about 729, that's the actual use of the shower, where the person was in the shower. The temperature was very steady. They only adjusted a few times. And then at 729, they turned it off. So that's the difference shows the difference between use, as we're calling it, and demand. The use is from 719 to 729, roughly speaking. The demand was from 723 to 729. So, over a third, almost a half of the use was not actually productive. And that's for showers. Next slide. And the same.
Jim, sorry to interrupt. You're getting close to time.
Okay, I'll talk fast. You got the same effect on washing, except sometimes you don't really wait for hot water. Next slide. This is a kitchen sink draw, the same two charts. You'll see that they used cold water up till about 10 minutes for washing, rinsing pans or something. At 10 minutes, they turned the full hot water on, but you'll notice it took until maybe about 12 seconds till they actually got hot water at the sink. That's the upper plot, the dark line, the solid line on the upper plot. And then from there on, most of the uses are a mix of hot and cold, because the water in the pipe's hot enough, they don't have to use, they're not using pure hot. And, they start using, so from then on, it's a mix of hot and cold, except for maybe one of them at about 13 seconds. And there's lots of uses, and they're intermittent. Next slide. This is about machines. I'll show an example of dishwashers. So keep going, except to note that the pipe sizing calculations are based on clothes washer water use from clothes washers in the field, and the draw rates may be quite a bit smaller. This is a dishwasher example. It's a different charting system, so it's a little bit more awkward to see. The flow rates are the rectangular slices. You'll see that, and the temperature at the dishwasher is the green line. So the key to notice is the first, you know, the first time this is all one load, one cycle. The first time the dishwasher calls for water, it's not hot at all, looking at the green temperature, the green line. The second one, it's, you know, reasonably warm, it's getting there. The third one, the same. The fourth and fifth, it's cooled off again, so it doesn't get hot water until the sixth and seventh one, or seventh and eighth. So just to notice that the dishwasher is not getting hot water all the time. In fact, hardly ever. Next one, next slide. The other problem with plumbing is especially in single family and perhaps more now in multifamily, pipes aren't usually shown on the plans. The architects aren't aware of the design implications. Obviously, the longer, the bigger, and the bigger the pipe, the longer it takes to get hot water out of the end of it. And I really want to give props out to Steve and Dan and Toju for updating all this stuff, but there's still a lot to do. And I think I'm close to done here. Just summaries. It's hard. Hot water use is hard to measure. Hot water demand is even harder to measure. They aren't the same. Hot water demand, what we expect and the way we actually behave depends on our experience with the system. Next slide. And then maybe we should start thinking about plumbing design based on demand. Maybe some uses should be cold water, dishwashers and clothes washers. Do we want to maybe make the sinks default to cold unless you actually want hot? And then a big question is, how do you get the floor plans to scrunch in so you don't have the long pipes that need to be fat to get the hot water to where they're going? And that should be it for me. So, Steve, back to you. Or
yes. Okay. Yes, Jim. Thank you very much. Appreciate that. And we're going to turn it over to Miriam now.
Anyways, my name is Miriam Blokker. I'm working with KWR Water Research Institute in the Netherlands. Some of you have seen previous presentations in this series, and today I'd like to explain a little bit more about how SimDame actually works. So how do we do the simulation of water demands in buildings? And my slogan for that is people are so predictable, so it's very easy to do. One of the slides that summarizes it all is this. It's a stochastic model, and you need stochastic model because water demand is not the same in reality. Think of your own water use today, tomorrow, or next week. It's slightly different. So you have to take that into account. We're using all physical-based parameters, so we have information on how often people flush the toilet, take a shower. We have also some information on typical inlet patterns for washing machines or dishwashers. And people's behavior is also in this. It's a small spatial scale, so we have a demand model per end use because you really are modeling showering behavior differently from kitchen tap or toilet flushing. It's also small temporal scale. It's down to 1 second, and of course you can aggregate from that. And it leads to realistic demand patterns. So if you compare two measurements, you'll see that it actually leads to something useful. So this is a slide that I borrowed from Steve years ago, and it's still the only slide I ever use with an equation on it. So this is how that works. For each event where you draw water, you'll have this block pattern with a certain starting time tau and an end time tau plus d of duration. with a certain intensity or flow rate, and everywhere else it's 0, and you can just add those. So you can add the different events, and that will lead to a total demand pattern. And this will be true for each pipe or the water heater or the water meter, or however you would like to aggregate. We have not been using flow measurements or input to get input data. We based it all on surveys. However, we are looking now into, can we use smart meter data to maybe get a little bit better estimates of the input data, input parameters, but we're not there yet. So far it's all based on surveys. So there are surveys on people's diurnal patterns. When do they get out of bed, leave the house, and then return home and go to bed? And typically, because people are so predictable, it's very easy to say that after they get up, they'll take a shower, flush the toilet, make a cup of coffee, and things like that. So we know how to sort of align people's behavior with people's water use or water demand. Now, you've all confused me, Jim. Of course, it's also important to know how often people use certain appliances or taps, and a toilet flush typically is about 6 per day, but this follows a nice Poisson distribution. And you would assume that a person would not flush it all 6 times within the same hour, so there's probably some variability over the day. We also have information on how long people took a shower, so this gives us some information on the duration of an event, and typical inlet patterns for washing machines or dishwashers, which also gives us information on duration and also on flow rates. So now that we have all the input parameters, we can do the simulation, and let's look at an apartment building for, in this case, 12 apartments. And there's a variation of how many people live in those apartments. And we're looking at the middle one with 5 people, so 2 parents and 3 kids. And all of the apartments have the same floor plan with a bath, shower, and toilet in the bathroom, and then a kitchen with a dishwasher, a washing machine, and a sink. And of course, it's an apartment building, so there is no outside water use here. So let's first look at how we model or simulate the demand at the toilet. And this is a bit of an old-fashioned one, which has a 9-liter cistern, and with a certain pressure, we can assume that it takes about 3.5 minutes to fill this system. We have 5 people. They all have their own time of when they go to bed and when they get out of bed and when they leave the house. So for each of these 5 people, we'll look at their individual behaviors. And we have that frequency of use, so we draw random numbers from that for each of those 5 people, how often they flush the toilet at this particular day. So with a random number generator, we'll get to a pattern like this. And if you would run this simulation again, you'll get a slightly different pattern, of course. And you can see that during the night when all of the people are asleep, there's only one person who wakes up apparently and has to go to the bathroom. But the rest you can see is during the day when most people are awake and actually at home. The next step would be to do this for all of the end users. So for your shower, your kitchen tap, your washing machine, etc. And the nice thing is that since you know the end use, can also extract information on hot water use, not just cold water use. So that black line is the total demand, and the red part is the part that is the hot water demand. Yes, demand, not use. And in this case, typically you would measure the black lines at the water meter and then the red lines at the water heater. And this is sort of a Dutch data set. So we have cold water running towards dishwasher and washing machines, not fed with hot water typically. So if you run this simulation again, of course, you get a slightly different pattern again. So if you do an analysis, you'll have to take that variability into account. You have to use that stochastic set of data. So you have to also compare your results if you want to do a validation to measurements, which is also a data set of several days. So you can do a comparison on statistics. And you can do scenario studies. And again, you need to look at the variability in your results. So again, use the stochastic demands and do a lot of simulations there. So for the validation, we did a lot of those at several aggregation levels. So we looked at a single home, but also at an apartment building, at non-residential buildings as well, and in the streets. So, and then we looked at average demand patterns, but also the maximum flow rates. So we know we can say something about design parameters that Steve has talked about. We've also looked at a variability in flow rate and a change in flow rates. We've looked at different time steps, so hour, 15 minutes, down to 10 seconds. We do not have measurements of 1 second. We also looked at applying this in drinking water distribution networks, and then we looked at water quality specifically, and we also did validation on water age and pulse shape of electric conductivity measurements. We looked at temperature. We applied it in sewers and measured water quality there and flow rates. So we're very secure about how well it works, but we have not done any validation at the level of the tap. So if we're talking about premise plumbing modeling, we have not really gone down to that specific level yet. Just to show you a few graphs, on the left here is a measurement in a street of 140 homes. One of the lines you see is simulation, the other two are 2 measurement days. And if I didn't tell you which was which, you wouldn't really be able to tell that one is typically a simulation result and another is a measurement result. They are very alike, and you can put that into statistical figures to say how much they are alike, but let's say they're pretty good. And then on the right, you can see average water demand patterns. So the variability was not shown here for cold and hot water uses and demands in apartment buildings, hotels, and nursing homes. And we also did in offices, but that was just cold water. We also look specific at maximum flow velocities, not going into that. And then what we did is we made a hydraulic model of a premise plumbing system. We have pipes going to each tap, and that's pipes with cold water and hot water. And then we applied the demand patterns from Syndeum for the specific end uses at those taps. So the shower, cold and hot water has a specific demand pattern, as does the kitchen tap and the washing machine and so forth. And of course, this shows you only one day, but we did, I don't know, several, maybe a week or a month with different demand patterns there. So some of the applications that we really went down to the level of the end use is looking at how demands change when pressure or electricity is insufficient. So if there's not enough pressure, but still some, you might find that the top level of the house has no pressure. And in the Netherlands, typically that's where the hot water heater is. So that would affect showering behavior, unless people want to take a really cold shower. So really looking at how that premise plumbing system is build up and what the effect of pressure is. That's what we looked at. We also looked at when electricity is not available, people would not use the washing machine, but they might still want to do some hand washing. So we really looked down on to the level of the end use to find what the effects of those different scenarios were. Another study where we really looked at end uses is gray water reuse, where we used SimDeum to estimate the production of light gray water from the shower, basically. And for that same household or the same apartment building, we looked also at the gray water demand at washing machines and toilet flushes. Another study was looking at energy use for hot water, where we looked at the water demand, also losses in pipes, and those waiting times that Jim also talked about are definitely part of that. And the electricity used in washing machines and dishwashers to heat the water was also taken into account. We looked at a variation of possible water heaters and how they would affect costs and CO2 and efficiency of use. So when we looked at those applications and not having validated at the level of the tap, I've come to realize that at this really level all the way down to the tap, it is important to, or it might be important, I'm not really sure, to take some extra interaction between user and the system into account, and only part of that is implemented. So for example, if there are a few people living in a house, they will not all be taking a shower at the same time. So we probably have to find that a person takes a shower and the other person has to wait. And that is actually implemented. We also might assume that people would not flush the toilet, all of the toilet flushes within an hour. So we'll put some minimum time between uses. That's also implemented. People typically or hopefully wash their hands after toilet flushing. That's not implemented. Users influence each other. They might share meals. They have to align in the bathroom for the use of the shower, and so they might be home at the same time, awake at the same time, and I have no idea. I think it is true, not always, but it's definitely not implemented, but it might affect the maximum demand, for example. And then also the influence of the premise plumbing system. So person wants to draw hot water, opens the tap, and then you have to wait for a certain time, depending on the specific system, till you actually have that hot water at your tap. So I think that's an important one to take into account. And the same could be said for maybe the pressure that's available, and that would influence the volume or the volume flow rate, and maybe even the volume of water use. Another thing I'd like to do, haven't done yet, is put SimDeum also into discharge patterns and look at in-home sewers, especially in apartment buildings. So some future use, we're working towards that, hopefully this year. And some other future work is that by the end of the year, we hope to have SimDeum available in Python as an open source project, and we'd like to see people contributing to that. Maybe contributing to SimDeum itself, or coupling with a hydraulic simulator, which could make it much easier to actually use stochastic demands in that simulator and look at the results in a stochastic way. So to summarize, SimDame can simulate water demand in the premise plumbing system, and it will give you residential, and we've also have various non-residential buildings that we've made and tested. And you can look separately at cold water and hot water systems. There is expected to be interaction between users and the system, and only part of that is implemented yet. Then would also like to test the use of SimDame wastewater discharge patterns, and have SimDame, PySimDame in Python, and I would like to welcome many developers on that. That was my last, that was my last slide. Thank you.
And I think we're ready now for our final speaker of the day. Stefano Alvisi will give us an update on the experience with COVID in Italy and has it impacted water demands. Stefano?
Okay, so let me briefly introduce myself. I'm Stefano Alvisi from University of Ferrara, and in this very brief talk, I will focus on a quite specific aspect, that is the impact of the COVID-19 on household water consumption. Indeed, we all know that household water consumption are affected by several different factors, such as socioeconomic, climate, or geographic factor. Some of these are more important, some are less important, but let me say that in the last month, we have seen that a new factor can influence household water consumption. That is the lockdown due to the COVID-19. Indeed, the COVID-19 had induced many countries to implement exceptional social distancing measures, to close school, university, and all this action had a significant impact on people's users, habits, and on water consumption consequently. In particular, Italy was one of the first Western countries hit by the pandemic, and the presence of two outbreaks in two towns of Lombardy and Veneto was confirmed at the end of February, on the 21st of February. Few days later, the government closed all the schools and activities in these areas. And let me say that on the beginning of March, on the 8th of March, the government announced the ban on travel from and to several regions in northern Italy, including Emilia-Romagna, Veneto, and Lombardia. And finally, on the 11th of March, we underwent a period of lockdown till the 4th of May. Similar situations were observed in several other countries, and in particular, we were already monitoring water consumption at household level by using smart meters installed at the inlet point of each house in a small residential district in Rovigo. That is a small town in Veneto, very near to Venice, and it is definitely one of the first regions seriously hit by the pandemic. We were already monitoring water consumption in these houses since April 2019. So we went on monitoring also during the lockdown, and we had at our disposal hourly time series of water consumption of around 300 users, 300 houses in this very small district in Veneto. So we could make a comparison of the water consumption at household level in the pre-lockdown period, in a, let me say, normal situation, and during the lockdown. We performed this comparison both by considering the total consumption of the DMA, but also by looking at each single user. In particular, by considering the total consumption of the DMA, we could see a significant increase of the water consumption in this small district. In this plot, I'm showing the daily water volume consumed by the 300 residential users from the beginning of February 2020 till the 4th of May 2020. In particular, here I'm also showing two important dates. The first one was the closure of all schools and university in the DMA considered. That was around at the end of February. The second one, on the 11th of March, was the beginning of the real lockdown in Italy. And by considering these three periods, let me say a situation before the disclosure of the pandemic in this city, in this transition period between the closure of all the school and the beginning of the real lockdown, and after the lockdown, we can notice that the water consumption, the average daily water consumption definitely increased. Someone could observe that this increase of the water consumption could be lead also to some sort of seasonal effect. Indeed, we are moving from February to May, we are moving from winter to spring, and in order to check this hypothesis, we made a comparison of the average daily volume consumed by the 300 users in April 2020, let me say during the lockdown, with the average daily volume consumed by the same users in the previous year, in April 2019. And we can immediately notice that the average daily volume of these 300 users increased from around 60 cubic meter to 70 cubic meter per day, with an increase that was around 20%. So being the period the same, the month of the year the same, we can definitely state that this increase is almost due to the lockdown. But the lockdown had an effect not only on the total water consumption of the DMA, but also on the pattern. Indeed, in this figure, I'm comparing the weekday pattern of the 300 users. It is an average pattern of the 300 users in the pre-lockdown period. I'm referring to the month of April 2019, and with the solid line. And the same, in the same period, the pattern during the lockdown, let me say in 2020. By looking at the pre-lockdown period, we can immediately notice that the pattern of this residential DMA was characterized by a very high peak in early morning, at around 6-7 a.m. The water consumption definitely decreased during the morning. It remained quite low during all the day, and we have a second peak in the evening. During the lockdown period, the pattern changed significantly. In particular, we can immediately notice that the early morning peak was delayed of around a couple of hours. It was at around 9 a.m., not anymore at 7 a.m. But, and this is definitely more important, it was significantly reduced. The hourly coefficient was more than 2 in the pre-lockdown period, and it was around 1.6 in the lockdown period. After that, the consumption remained definitely higher during the morning. We can notice some sort of small peak at noon, and during the evening, the situation is almost equal to the pre-lockdown period. Some changes were observed also for other kind of day of the week, but definitely less evident. For example, on Saturdays, once again, we can notice that the early morning peak was some way delayed. The consumption remained higher during the morning, but the difference was not so marked as during the weekdays, whereas for Sundays and holidays, the situation was almost the same during the pre-lockdown period and the lockdown period. Clearly, this is due to the user habits, to the different kind of activities performed by the inhabitant of these houses. And thus, we tried also to consider not only the total set of users, considered all together, but also single users, single houses. And we performed an analysis of the pattern of each of these 300 houses. To perform this analysis quite rapidly, we performed a cluster analysis. Thus, we applied the K-mean algorithm on the set of average daily consumption pattern of these residential users, considering both the pre-lockdown period and the lockdown period. In particular, we consider three clusters, and in this figure, I'm showing with the black line the reference pattern of each of these three clusters, whereas each of the colored line represent the typical weekday pattern of each of the 300 users. In particular, the three clusters are highlighted by quite a different profile. The first one is a profile with a very limited consumption during the day and a significant peak in the morning. The second cluster is characterized by a profile with a moderate consumption during the day, quite higher than in the previous case, but a smaller peak in the morning, even though the highest peak of the day is still in the morning. Finally, the third cluster is characterized by a moderate consumption during the day and a peak in the evening. Well, it was quite interesting noting that in the pre-lockdown period, that is referring to April 2019, 25%, 1/4 of the users belonged to the first cluster, 37% to the second one, and 38% to the third one. Whereas during the lockdown period, the cluster remained the same, but the percentage of users belonging to the first cluster was definitely lower, around 10%, whereas the number of users belonging to the second cluster increased significantly to 50%, and the number of users belonging to the third cluster remained almost unchanged, around 38–39%. This is even more evident by looking at this table. In this chart, each line refers to a cluster in the pre-lockdown period. The first line refers to the first cluster, considering the year 2019, the second line to the second cluster, and finally the third line to the third cluster, whereas each column refers to each cluster in the lockdown period. Clearly, the numbers along the diagonal of this chart represent the users that did not change their consumption category from the pre-lockdown period to the lockdown period. And we can state that around 60% of the users did not change their consumption category, moving from the pre-lockdown period to the lockdown period. But let me say that 27% of the users changed their consumption category. And in particular, the majority of these users, about 70%, moved from the first class to the second or third class. And this is quite evident if we try to think to the impact of the lockdown on users' habit. Unfortunately, we could not monitor each single end use, and we could not perform clearly during the lockdown period surveys to these users. But we can take a look at these two tables, two charts, that represent quite a typical situation of a family with two parents and two children. Both the parents are working, and in particular, one of the two still worked in his office during the lockdown period, whereas the other one, during the lockdown period, had to work at home, homework. The two children were both attending school, but during the lockdown period, they had to attend the lesson staying at home. If we look to the typical situation in the pre-lockdown period, let me say in April 2019, we can immediately notice that both the parents typically wake up at 6:30, 7 a.m. They use water in the bathroom for having shower or using bathroom tap, and after that they prepare the breakfast and have breakfast. The children wake up slightly later at 7:30. Once again, they use water, but we can immediately notice that, for example, for this family, water is used within the house in several end uses in a quite narrow time period, from 6:30 till 8. At 8, all the members of the family have to leave the house to go to work or to go to school, and they clearly not use water during the day, during the morning, or in early afternoon, and they start once again using water during late afternoon or in the evening. During the lockdown period, the use of the water for one of the two parents remained the same, because once again he had to wake up at 6:30 and use water as he was used to do in the pre-lockdown period, whereas the other parent that had to work at home waked up slightly later. Maybe he had breakfast together with the husband or the wife, but used the water in the bathroom later, for example at 8 a.m. And similarly, the children waked up later, since they started the lesson not at 8:30 but slightly later during the lockdown period. Once again, we can immediately notice that even though the end uses involved during the lockdown period were the same, the use of the water was somewhat spread over a longer time period, from 6:30 till 9 a.m. And furthermore, we can immediately notice that water was also used during the morning or at noon for preparing lunch. Thus, this has an impact on the cumulative distribution of use of water in this house. And this was confirmed by the analysis of the sampled cumulative frequency distribution performed for each of the 300 users. Here I'm showing the sampled cumulative frequency distribution of the water volume consumed during the weekdays in one house in the pre-lockdown period and the lockdown period. I will just show a couple of this situation, not all the 300 cases, but these are quite significant. For example, we can immediately notice that both in the pre-lockdown period and the lockdown period in this house, no water was used during night hours. The cumulative frequency distribution is characterized by almost null values, 0 values. In the pre-lockdown period, the blue line, water was significantly used in early morning hours at 6 a.m., 7 a.m., whereas during the lockdown period, the cumulative frequency distribution is once again still characterized by 0 values at these hours. If we move later on, we can immediately notice some sort of shift between these two cumulative distributions. The red one, referring to the lockdown period at 9 a.m., is characterized by definitely higher volumes than the blue line, which refers to the lockdown period. If we move to this other user, it is quite interesting notice that in the pre-lockdown period, once again, this user used water at 7, 8 a.m. more than in the lockdown period. The blue line is shifted toward a higher volume than the red one. But if we go on during the morning, we can immediately notice that for this user at 9 a.m., 10 a.m., he rarely used water because the cumulative frequency distribution is characterized by almost 0 values. Whereas during the lockdown period, we can observe many values different from 0 and around 50 or 70 liter per hour. Clearly, this is a demonstration that the lockdown had an impact on the household water consumption, and in particular by making reference to the previous presentation of Stephen and Miriam, clearly this impact on the probability distribution that should be used to evaluate the peaking coefficient, or more in general, to simulate the household water consumption. Thus, summarizing, we can state that at least for this district in Italy, but let me say that this situation was quite common also in other residential districts here in Italy. The lockdown had the effect of generally increasing the residential water consumption. Very important, the morning peaks were delayed, and let me say that in Italy, morning peak is the most important peak during the day, and these morning peaks were significantly reduced. And this had an impact also on probability distribution of hourly water consumption that were significantly modified. Clearly, we should need more data to generate this result, and monitoring of end use would be of great interest, but in this situation, we could not at our disposal this kind of data. And let me say that that's all, and I would like to thank also my collaborator and my research group for supporting me in collecting and analyzing this data. That's all. Thank you very much.
Okay, fantastic. Thank you, Stefano. And I'm looking at the clock, and I see that that 90 minutes this morning passed by very quickly. So I want to propose the following thing. We obviously don't have time really for any questions directly to the speakers. I would, however, encourage folks that may have questions to just put them in writing and to send them to myself or to Jun-Suk Lee, and we'll make sure that they get to the speakers and we can get some comments back to you. I also want to thank, speaking of the speakers, thank all of them for doing a fantastic job today. Jim Lutz for providing some insights on the hot water use, for Miriam Blocker on the overview of her very powerful water demand simulator, Simdium, and Stefano for sharing with us the experience in Italy with the COVID-19 virus that we're dealing with, of course, in a very serious way right now in the US. The panelists, sorry that I didn't manage the time properly today, so we really didn't get to any of the panelists, but I know that you were on standby, and I appreciate that very much. If you are interested in taking a quiz, I would say stay online after 11:30. We'll put the quiz up there, and then you can take it. There's 4 simple questions, multiple choice, and then we'll get the solutions out to you here in the near future. So with that, I want to go and take control of the screen just for a second, because I want to announce the next topic. Here we go. So I'm getting to that. So yes, please make a note that the monthly seminar series is going to continue in August. Going to be organized by Professor Jun-Suk Lee. The topic is going to be hydraulic modeling of premise plumbing systems. And I hope you can join us again for that on Thursday, August 27th. So that's the plan for the one coming up in the next month. So with that, I guess I would thank all of you for your attention. And again, please encourage you that if you have questions, feel free to send them to me. I will forward them on to the speakers, and then we'll get them get some responses back to you. And those of you that are interested in taking the quiz, please stay online, and we'll make the quiz available to you here very shortly. So if you're still with us, this is an optional quiz based on the material that was discussed this morning. It's, I think, a fun quiz. There are multiple choice questions, 4 of them, 1 from each of the 4 speakers. Each question has 3 answers, so it's either A, B, or C. And what I would suggest you do is the following. Just write your answers down on a piece of paper. So you'll have 4 questions, you'll have 4 answers of A, B, C. And so for instance, you might see a string that looks like A, C, B, C as a possibility. Then when you've answered all 4 questions, then just load them into the chat. And so you'll give away your anonymity, but that's okay. Load them into the chat, and then we'll publish. We won't publish, but we'll just announce how the questions were answered in general. So here's the first of 4 questions. It has to do with the presentation that I gave, and we introduced a new concept, a new dimensionless number called the Hunter number. And 3 possibilities. It represents either the total number of water conserving fixtures in the building. It represents the probability of stagnation, that is no demand during the peak time in a building, or it's the average number of fixtures that are simultaneously running water during peak time in a building. So one of those 3 choices is the best answer, A, B, or C. Please make your choice, and we'll go on to question 2. Question 2 comes from Jim Lutz's presentation on hot water use. So on average, the amount of hot water used each day by a home occupant is most nearly, and we have 3 possibilities, A is 5 gallons per person per day. B is 15 gallons per person per day. And C is 45 gallons per person per day. One of those is the single best answer, A, B, or C. So please make your choice. And then we'll move on to the third question. This comes from Miriam's presentation on her water demand model, Syndium. And we heard it's designed to simulate residential and non-residential water demands. The question is, does it do it A, on a minute-by-minute basis or finer? Does it do it on a day-by-day basis? Or is it set up to run on a month-by-month basis? One of those three choices is better than the others. So please make your selection. And then we will move on to the fourth and final question of this pop quiz. So this is from Stefano's presentation, which we just heard on the case study of the COVID-19 lockdown in Italy. And on the average, what did they discover? That A, there was an increase in both the total daily household consumption and the daily peak coefficient. B, there was an increase in total daily household consumption, but a reduction in the daily peak coefficient. Or C, a reduction in both household consumption and daily peak coefficient. I think his question is the hardest one of all. So you've got the three choices, A, B, or C, regarding the water demand behavior from the lockdown in Italy. And please make your choice. And then if you're inclined, you will have solutions A, B, or C for 4 questions. Feel free to add them to the chat. We'll compile them. We'll make a determination of what was the percent correct. And then we'll just shoot a note out to everyone that attended so you can see how you fared. I will keep everything anonymous. You won't have to worry about your performance being shared. And we'll share that with you in the near future. Okay, so we'll summarize the results on the quiz. We'll push that out and let you know how you did and what the percent correct was. Again, I want to thank Bill and Tara for helping to run the show today. I appreciate Toju and Jonathan Burkhart being on standby for the panel session that we really didn't have. And then in particular, I want to thank Jim Lutz, Miriam Blocher, and Stefano Alvisi for their fantastic presentations on water demand. Very informative. I hope everyone learned just a little bit. And I truly appreciate the audience that stayed with us for the full 90 minutes. So thanks again for your time. And we'll see you, we hope, in about another month for the 4th webinar in this series that deals with premise plumbing hydraulics. Thanks again and take care.